I can't get into it. I'm gonna draw like the coolest Earth you've ever seen. Ready? Oh yes. Remember, it's a sphere. Earth is a sphere. Don't flat Earth me, okay? Really, don't do that to me because there are kids in this building who don't know that you're joking, and don't understand that you know that you're joking. And so let's stop that stupid. It's so frustrating to see these garbage YouTube videos because we. Have you watched them? What? Don't watch them. They're a waste of your brain power. You have a limited number of minutes on this earth. Choose good things to spend those minutes on. The earth is so much of a sphere, you can't even understand how much of a sphere it is. Yeah, you can measure the evidence that shows that it's a sphere from right here. We could do the experiments. It's really nice.
And you can just look.
I don't have time. Yeah, you can also just look at it. Okay, sorry. We're here. So Earth is a sphere. That's like a fact. That's an observable fact. We can see it. Not only can we see it, but it explains like a ton of things that we see happen. Anyways, what does it mean to be in space? We're going to start instead with a stupid cartoon of a cannon. Are you ready for my cannon?
Yeah.
Check this out. Yeah. It's on a mountain. Yeah, you've seen this, Dylan. It's on a mountain. Do you see that mountain? It's the biggest mountain on Earth. Which one's that? Yeah, well, Everest goes the...
Jasmine!
Kilimanjaro is the biggest in Africa. That's a big one, but there's bigger ones than Kilimanjaro. Everest, although Everest, if you're talking from the bottom of the mountain to the top of it, Everest is not the biggest mountain.
It's the biggest mountain underwater.
Everest is the tallest above sea level. Mauna Loa in Hawaii is the biggest mountain because it goes all the way to the bottom of the ocean floor. Anyways, this is an imaginary mountain, real tall. I'm going to shoot my cannonball exactly horizontal, totally sideways, right? If we shoot it totally sideways, gravity will pull the cannonball down, right? And so you would see a path of the cannonball like beep. Is that fair?
Yeah.
Okay. Let's say we shoot it a little faster, like real fast. And we can shoot it so fast horizontal, it's still getting pulled down, but it will go over the horizon and land over the horizon. Could we imagine that?
Oh,
so it's like totally sideways and gravity's pulling it down, but it takes a longer time to land. You following? What if we shot it so fast? Remember, I'm shooting exactly sideways. Gravity's always pulling it towards the center of the Earth here. That it took like a long time for it to hit the ground. Or what if I shot it sideways and it took like halfway to hit the ground? Or what if could I shoot it so fast? Remember, gravity's always pulling it in towards the center, right? What if it was so fast that it came all the way around and landed like right there? What if I shot it so fast that it came right backwards around? Remember, gravity's always pulling it in towards the center, and it came and hit. That's where the metaphor breaks, hitting the back of the cannon. But could that, like, theoretically, hypothetically, could we do that?
Yeah.
Well, okay, there's a
go out of the atmosphere.
Oh, you see the issue? We can't have the cannonball here in the air, right? Because as soon as we shoot the cannonball, what does the cannonball start to fight?
Gravity. Air.
It's fighting the air resistance. So you got your cannonball, like, but it's slowing down through the air. So where do we have to put this hypothetical cannon? Where do we have to get it to? So we get this cannonball up here above the atmosphere, and we shoot it sideways so fast that remember, it's being pulled towards the center of the Earth, always towards the center. And it's being pulled, you see it being pulled towards the center? Yeah. But it's going so fast that it just keeps missing the Earth. That's like the moon? That's called an orbit. That's what orbiting means. It's being pulled, it's still in the gravity, it's being pulled to the middle, but it's going so fast it keeps missing the side. Now, what if it goes so fast that it escapes that gravity's pull? Could that happen? Yeah, it could go too fast and be like, boom, and it's gone. Right? Or could it go too slow? If we're talking the International Space Station, or an astronaut in their capsule, and they could slow down accidentally, and then they get caught, and then it's like...
Hasn't that happened before, though?
Yeah. The Russians had a space station that started going a little too slow, and so it came down a little too low, and then it got in the upper atmosphere, and it started to hit the air particles, and it slowed down, and then... Skylab also happened to the United States space station. Our first space station, Skylab, crashed. No, they knew it was going to. They planned it. The International Space Station is in a stable orbit.
Could it be in the stable orbit and then like get out of orbit?
It's in a stable orbit, so the physics of it are just keeping it spinning, which is kind of neat. Ooh, wait. How fast do you think you gotta go to stay in orbit like that?
Pretty fast.
I know the answer.
Do you?
Last year.
What about how fast is the space station?
How fast?
1,000 miles.
17,000 miles an hour. Have you ever seen a rocket launch like the space shuttle launches? Do you notice they go up, right? But do they only go straight up?
I don't play baseball.
What do those rockets do really quickly?
They turn.
Yeah, they roll. It's called the rollover. They roll over, and then so the rocket, it's shooting up to get up above the air, but then really quickly it's like, nope, we need to go sideways. And so about half of the rocket burn is actually getting it going really fast sideways. About half of the fuel is to get up, the other half is to go fast sideways.
Well, it's like rise and run, like this.
Yeah, but they do it like a, and so it's, okay, wait. Oh, wait. So are the astronauts in gravity?
Yeah.
Yes, but
Yes.
Yes.
what are they doing in that gravity? Henry,
Free fall.
they're falling constantly. Remember, they're going sideways real fast, and they fall, and as they fall, they just keep missing the Earth. They're in free fall. Imagine being in an elevator that drops.
Oh my god.
Your stomach's going to rise up, but there's going to... Let's say that there's no bottom to this elevator, just for my sake. And you're in the elevator, right? And it's a totally smooth ride. What are you going to do in that elevator? Everybody in the elevator is going to be floating together. Will you have any sensation of falling? If the elevator is totally smooth, and you can't see any outside thing, you can't tell that you're falling. You're floating, you're like, why are we floating? And if it's an elevator, it's like you're falling. But the astronauts, they're out in space and they're falling in free fall in this orbit, so they float.
That's so cool.
Isn't that awesome? Yeah. Wait, oh, so do they have weight in space?
Mm-hmm.
Technically, yes.
Yeah. In this case, we call it, they'll say like microgravity, or they're like weightless. They don't have any weight there. But do they have mass?
Yes.
Totally. Okay, wow. That was a distraction. But interesting. Oh, on the moon. Do you have weight on the moon?
Yeah, but it's really.
As much as here?
No.
Because the moon's gravity is smaller, so it pulls you a little less hard. So when you walk on the moon, it's like boom, it's really awesome. Someday we'll get there, you guys. We've already been there, but someday we'll go back, is what I mean to say. Turn to your density notes, please, the density side. Oh, go fast, go fast. You know, they're thinking that they might skip the moon and go straight to Mars. Elon Musk just announced a plan to send manned missions. Hopefully, I think they're looking at 2020 or 2024 for the first missions. Now, 2020 they're going to send unmanned, like supply ships. 2024 they're going to hopefully send manned ships. That's an ambitious goal. It'll probably be delayed a couple of years, but seriously though, the future astronauts. Did we talk about that?
No.
Probably the first people on Mars are currently middle school students.
Yeah, me. Oh, I want to go.
Me, but not.
Start studying up science, math, biology, science. You got to start studying up, or be a fighter pilot. These are your routes. Oh, if you can hear me, clap one time. If you can hear me, clap 2 times. Okay, so density. What is density though? It's the yeah, but we need to define it without that. It's the amount. I'm going to say the amount of stuff. Again, stuff, if you are ready for the more fancy words, it's actually the amount of mass, which is the amount of matter. The amount of matter per unit of volume. So it's how tightly packed the matter is, and also how heavy that matter is density. Density is like how tightly packed the atoms are.
Why? I hate that. Like haunted in here.
But these actually recording, right?
Yeah, I hope so. We've got an equation also, right?
Yeah.
Isn't it density equals like something over x or something like that?
It's something over something. Density equals,
We learned this once.
yeah, it's density equals mass.
Over volume?
Yeah. Get that recorded. The short version, just the letter version of that, is D equals M over V. Density equals mass divided by volume. Okay, we gotta talk units too though, because we're always talking about units in my class, because units matter. What do we measure mass in? Grams, right? Or kilograms, but let's go with grams for a minute. What do we measure volume in? Cubic centimeters, so we got cm cubed. Oh, that's our units, you guys. It's the mass per unit volume. Your units are going to be grams per milliliter, or you could go grams per cc, or grams per... These are all ways of saying the same thing, but they'll get used a little differently. You could, if you're, the official units would also maybe be kilograms per meter cubed. That can also happen, depending on what you're studying. Each industry will have its own norm. Yeah?
Don't we usually use rho, not d for density?
We as in you? Yes. We as in ninth graders? No. We'll use D in this class. If you want to use rho, I will know what you mean. But I'm not going to teach that to ninth graders.
Is that,
Say that again? Oh, that's my kg.
like, what did you say, row?
Rho, yeah, it's the Greek letter rho. Which is a common, like, you know how, like, certain units will get, like, their own special letter? Yeah, a lot of, like, physicists and stuff will use the Greek letter rho for density. But it's just an extra confusion that I don't add on for ninth graders yet. When you take physics in high school or AP physics, you'll use it. Density. So this object here, we're showing the particles. Can you label the particles? They're particles. Or you could go, maybe they're atoms, maybe they're molecules, but they're the particles that substance is made of. And you'll notice here we're starting really dense, right?
That's a solid.
So this is more dense. Yeah, we might say that they look arranged as a solid, I would agree. But we're going to range from more dense to less dense in this diagram. And that's kind of showing here the atoms are really packed in close. Here they're a little more spread. Here they're more spread out. You might also notice we've got like a regular gridded arrangement. That's probably a solid. Here they seem to be flowing around each other. That's going to be a liquid. And they're spread out. They'd actually be like flying around if they're a gas, right? Yeah, and these guys would actually be moving around too. But these guys are just wiggling in place. Now you guys have the example problems, right? Excellent, I have that as well. First of all, let's talk about the 8th grade love story. Density is an 8th grade love story. Density equals, D equals heart, 8th grade love story, but what happens to all 8th grade loves? Look at it, do you see it? Do you see it?
Oh!
If you forget how the formula, density is an 8th grade love story. D equals heart slash. You get your heart slash.